Hello friends. So in today's question, to transport a series of bundles of shingles A to a roof, a contractor tries a motor-driven lift consisting of a horizontal platform BC which rides on rails attached to the sides of a ladder. The lift starts from rest and initially moves with a constant acceleration A1 as in figure. The lift then decelerates at a constant rate A2 and comes to rest at D near the top of the ladder. Knowing the coefficient of static friction between the bundle of shingles and the horizontal platform is 0.3, determine the largest allowable acceleration A1 and the largest allowable deceleration A2 if the bundle is not to slide on the platform. So this BC is the platform and A are the shingles, and this lift is traveling upward with the acceleration of A1 initially, and finally it decelerates and stops at point D, and the angle is given as a 65 degree. So in the first part, we can say case 1 for acceleration A1. For acceleration A1. So let us draw the free body diagram for these shingles. So we have an acceleration which is A1 at an angle of 45 degree. Sorry, not 45, 65 degree. Okay. So it means it will be a force will be acting along this same angle 65 degree, and whose value will be nothing but the mass MA of the shingles and multiply by A1. So we can divide it into two components. So this will be our MA1 cos of 65 and a vertical component that will be MA1 sine of 65. And we are going to have, okay, so these are the forces. Okay, so we can just once again draw it with respect to the, you can say, friction and other forces. So it is going to have in the downward direction MAG, and there will be normal upward, let us suppose N1, and we already said that there is a force acting along the horizontal, and let us that force is being represented by F1. So because of this force there will be opposite frictional force, let us call that FR1. Okay, so these are the various forces which will be acting on it. So if it says that the bundle should not slide on the platform, then you can say for the bundle do not slide on the platform, bundle do not slide on the platform, F1 should be equal to F1, or which will be equal to mu static into normal N1. Okay. And can also write the equation. Let us draw it here. Let us represent it by a dot. So this will be N1, and we have M1 MEG in the downward direction. In the upward direction we also have MA1 sine of 65. Okay. So for the vertical motion, we can write that equation, that N1 minus MEG, and it is going to produce MA1 sine of 60 degree. From here we can write our equation for N1. So N1 will be equal to MA, we can take it as common, so this will be G plus A1, 65, so sine of 65. And we also know that along horizontal direction, okay, so we have a force F1, and we have also MA1 cos of 65. So from here we can say that our F1 will be equal to MA1 cos of 65. Okay. And we already know the value, so we can write here from that this implies that MA1 cos of 65 is equal to mu s into N1. We already know value of N1, so we write mu s. N1 is given as MA G plus A1 sine of 65. So this MA cancels out. We get A1 is equal to mu s is given as 0.3. G is our 9.8. And this will be plus A1 sine of 65. Okay. Yeah. Let me write it. A1 cos of 65. So we can just solve it. We can take A1 as common. We get cos of 65 minus sine of 65 is equal to .3 into 9.8, and A1 is equal to 0.3 into 9.8 divided by cos of 65 minus sine of 65. So this will be coming equal to as 19.53 meter per second square. We can say that A1 is equal to 19.53 meter per second square, and it will be at an angle of 65 degree. This is your A1. Next is for deceleration, that is case 2. For deceleration A2. So once again we can draw the free body diagram. So we have this MA A2, two components. We have MA A2 sine 65, and this will be MA A2 cos 65, because this angle is 65. Okay, and along with this there will be normal N1, and we have in the downward direction MA G, and we have here FR2, or we can say, yeah, let us suppose write FR2, doesn't matter. And there will be a force, let us suppose that is F2. So from the figure we can see that our F2 is equal to FR2, which is equal to mu s into N1, and we can also write the equation that N1 minus MAG is equal to minus, because the deceleration, this will be equal to MA A2 sine of 65. From here we can write our N1 is equal to MAG minus MA A2 sine 65, and our F2 is equal to MA A2 cos of 65, which is further equal to mu s N1. We already know value of formula for N1, yeah, rather equation. So this is mu s, we have MA G minus MA A2 sine of 65. So our MA cancels out throughout. We are left with A2 cos of 65 is equal to mu s G minus mu s A2 sine of 65. Here I missed, yeah, I missed here mu s, my mistake. Mu s, and this will be mu s. Okay. So this can be written as, sorry, taking A2 as common. Taking A2 as common, we are left with cos of 65 plus mu s sine of 65 is equal to mu s into G. So we have A2 is equal to mu s is about 0.3, 9.8 divided by cos of 65 plus 0.3 sine of 65, and this will be coming equal to as 4.24 meter per second square. Okay, so you can see our A2 is equal to 4.24 meter per second square, and at a direction downward 65 degree, and this will go A2. This completes the question. Thank you.